So we can start now, Hana?
Good afternoon, everyone. So our next speaker is Dr. Rashi Agarwal. Dr. Rashi Agarwal ma'am is from IT department, CSJMU. She has worked previously in ST Microelectronics, Noida. After getting a doctorate in computer science and engineering in 2006, she joined Chhatrapati Sahuji Maharaj University, Kanpur, as the head of the engineering and information technology department. She is having more than 15 years of teaching experience. Her research interest includes machine learning, computer vision, image processing. She is having more than 30 publications in Scopus and SCI Index journals. She has also authored the books, for example, is Starting Out with Python in 2016, and it was published by Pearson. She has also authored the book Computer Organization, which was published by ACMA Learning Private Limited. She is also having a YouTube channel, and it is based on the image processing using MATLAB, and it is having the more than 30 lakh views and is also having the 15K subscribers. So over to you, ma'am.
Thank you, Pratik. So it's a pleasure to hear such nice things about myself. Thank you. So let's start with the session now. So I'll just share my screen. Is it visible?
Yes, ma'am. Yes, ma'am.
Okay. So rather than going back to starting with neural networks, you've already understood what deep learning is all about. So I will move on to the part of CNN, which is specifically this topic, convolutional neural networks. So when it comes to CNN, let's first talk about traditional programming paradigm that we had. So we used to have rules, we used to get data, and in traditional programming, we used to make programs and get answers out of that program, right? Now, suppose I want to solve this kind of an activity detection using this traditional programming. I'm asked to find out whether, looking at an image, whether I'm walking, whether I'm walking, running, or biking, or maybe a golfing. So what will happen in a traditional paradigm, I can say if my speed is less than 4, I am walking. If my speed is less than 4, status walking. Else, if it is larger than this, I'm running. So still lesser than 12, between 4 and 12, it is running. If it is more than 12, I'm biking. So this is a very loose kind of an activity detection algorithm. And I will definitely not be able to get results that I'm looking for using traditional programming. And golfing, how do I detect? It's not possible for me to understand also. So for this, it comes in machine learning. What is happening is now I have my answers, I have my data, and some rules are being made now, which is basically being outcome by this machine learning approach. So this paradigm now gives me rules instead of giving me answers. So there are models built, and from this model, I'll be able to understand what activity I am doing. So that's the idea of machine learning. So this is the kind of output I will start having, looking at the images, the processing of the images. I can start getting certain patterns here, which I will recognize and say that, okay, this is a walking image, this is a running image, this is a biking image, and this is maybe golfing. So with this, it becomes simpler. So getting patterns is what we are looking at. Now let's look at a small problem here. Suppose I give you an example. I have an X with all these values, -1, 0, 1, 2, 3, 4. And I'm given a Y, and I'm asked, okay, try and understand what is the relation between this. Since we are all mathematical background students, we understand that this is going to be a function, and we start guessing. So what we do is make a guess. And I know this is a linear function, so I'll say y is equal to mx plus c. I'll put in some value of m here, some value of c here, or whatever you want to say, AX plus B. So I'll guess an A and B here, and I'll try and see the difference. Right? So this is what I will do. I will make a guess, check how far my accuracy is. Then I will optimize my guess and again keep repeating till my accuracy is got till the place I desire it to be. Right? So this is what we do in machine learning. This is a very, very simple approach, simplistic approach. So suppose I take y is equal to 3x minus 1. This is the output that I will get for this x. And I can see how different it is. So my y is this and my real y is this. So probably at one point I'm just able to match it. Otherwise there's a difference. So let's try and measure this. So this is my real value, the blue one. My green one is my guess. And I try and find out the difference. So this is the difference. If I add it up, I'll be ending up adding, and so minus 1 will get cancelled out with plus 1. And I will have an error of 2 plus 3 plus 4, which is actually wrong. So what we do is we take the squares of these errors. We square them up and then add them. And then we find out the square root. So since an error is always, it should be taken in a modulus form, that is why we take the square of the errors. Then we take another guess. Then we know that, okay, there's still a difference. Then we keep repeating till our error is reduced. And at 2x minus 1, I am able to get the perfect model. This is where I stop. So deep learning also works in the similar fashion. What we have is, we have for a simple linear regression problem, I will start with a weight here assigned to the neurons. So over here, there will be certain weights which will be trained, and there's a gradient descent in the sense that you take a partial derivative of the loss with respect to the weight. So you're basically looking at the tangent. So if you are here at the negative side, the negative slope will basically add up and I'll move towards positive. If I'm here on the positive side, a positive number would be subtracted and I'll be decreasing the weight. So I have to reach the global minima here, which I'm able to do using gradient descent. So that's the simplest form of problem. Now let's look at the practical part of it. I have certain examples for this so that you are able to understand this using just take a second. Right. So here, let me start by saying exploring the loss. So I'm just writing a very, very simple equation here. I'm importing the math library, giving a weight and a bias. This is what we call in terms of the y is equal to mx plus c. So my weight will be m and my c will be the bias, which you people have already studied in the previous lectures with various faculty. So x and y is what we have. And what are we doing? This y is basically, we are appending this into a list here, and we are multiplying w into this x plus b and putting it into this new list here, my y. So my y is getting, according to the guesses that I make of w and b, I'm able to find out the difference. And my square error is taken out here, yi minus my y. Basically, I'm trying to find out the difference of the estimated value, the actual value, squaring it up, adding this value, and then taking the square root to print out the error that I have. So this is my loss that I was evaluating here. I hope it's clear. So the evaluation of the loss that we had here is being done in this file. Is this okay? Now let's try and minimize this error. So what are we doing? We want to minimize this error. So we will simply make another program. Now here we are using a calculus to be able to use gradient tape. So like I said, gradient descent is basically using what? It is using the gradient here. That is the del loss by del the weight. So that is my gradient here. So the gradient tape is kind of taking this value automatically. You don't have to worry about it. There's something called gradient tape available in TensorFlow. And if anybody is interested, you can go to this file here and see the details of this gradient tape. All these files, by the way, are in your classroom. So anybody who wants to access, they are already there in the classroom. Please try and run them and you will be able to get the same results. Now what here we are doing is that we are taking the gradient here, and with the loss that we have, current loss is the loss between the model that I have made and the output that I desire, I have created a gradient of the loss. And then I'm trying to take a learning rate, which is generally a small value. We can initialize it. All these are hyperparameters which can be tuned for a particular performance. So learning rate, I just multiply the dW with that learning rate and assign these new weights W and B to the model. And after doing this, we generally have a learning rate. Like I said, it is a value which is specified. I make a model and I have epochs. So epochs is how many times does the entire network run. So how many times will I see the entire data set? Because I'm talking about the entire data, because there may be batch sizes also. So the number of times you see the entire data is the number of epochs that you have. So after this, you are basically training your model, and I have specified epochs to be 50. So 50 times this will keep of iterating again and again. And here you can see the loss is being minimized using the gradient descent in every step. And when I reach 50th epoch, I have this loss. And you can see the weights are 1.98 and B is minus 0.93. Whereas my actual values were 2 and minus 1, if you remember. We saw it here. 2x minus 1 was the perfect answer. So this is pretty close to what we wanted. We have been able to get it here. And to be able to see how it goes, we just generally plot how the train values actually change. So we are trying to minimize the loss using gradient. Now, this works fine. Now let's come to the neural networks. So this was working for a simple regression problem. Right now we saw a simple regression problem. Let's try and see other problems where this can be utilized. So I'm trying to make a single neuron network now. So first neural network will just have a single neuron and it will look like this. So it's a simple neuron. It will have an input X and an output Y. Here, now I start initializing my model as sequential. So sequences, when I have all the neurons adjusted in sequences. So for first sequence, first layer, second sequence. So this is a sequential model. There may be non-sequential models where, they come in later in stage. You'll have some classes of that also later in the course. So this is a sequential model. And I say Keras layers dense. So dense is where I'm basically connecting every unit to every unit. Right now, I just have one unit and just one single neuron here. The shape is a single array. So this is the simplest of all neural networks that I have. Now there's something called an optimizer and a loss, which you people have already studied in the previous lectures. So I will use a stochastic gradient descent here, and the loss is mean squared error. I'm trying to minimize this loss using the optimizer SGD. Again, I will fit this. So let's see how this works. Using this first neural network, I will import TensorFlow. Run this here. And now my model will fit the input with the output and the epochs is specified. So I'm not looking at the gradient descent now, this gradient tape now. I'm using SGD here as an optimizer and I'm using loss here, which I want to minimize. So I hope this is clear. And it's simply, I want to predict, suppose I put in 10, I'm getting 18.97, whereas actual model would have 20 minus 1, 19. So this is pretty close to what we want. And we have been able to realize our linear regression using a simple neural network. Now let's move on to a little complicated ideas. So this is what we've been doing. Now we are revisiting the problem again. And I say that, okay, I want to improve this. So what do I do? So again, the first part is just the same. We have the same model here right now. Now, instead of having just one layer, I have two layers. So this is what I had got as the output. Still fitting. Any questions in between? Please feel free to ask if you have any questions. Now you can see the weights that I got. So this was 1.997, which was 2 actually, and instead of -1, I got -0.99, which is pretty close to the actual values that we have. Now let's train a two-layer network to see if I get a better value. A two-layer network would look like this. I have 2 neurons here in first hidden layer, and then over here I have another layer, output layer. So here I'm defining my first layer as a dense unit, a dense layer with 2 units and 1 input shape. This one. The second is single unit. And then I take a sequence of all these. So I stack them up sequentially, these 2 layers. I compile them, and my optimizer and the loss are still the same. Let's see how this performs. So this is closer to what we wanted. This is very, very close to 19. Any questions, anybody? Optimizer, Vishal, are you a student of IT department?
Yes, ma'am.
Acha, so what I'll do is, because the audience here is a little, maybe from outside also, so I will explain this in the class only, but because the previous lectures have been taken on optimizer, but you can just understand that there are various optimizers available and we are using this one right now. Actually, this has been discussed before. If I start moving into that, I will lose track of this session. So I will explain it in the class.
Okay, ma'am.
Yeah. Right. So now you can see the predicted values closer than what we had got here. So yes, my two-layer network, the neural network, is performing better. And I can start seeing the weights also assigned to each and every value here. So you can see here I had some weight here, some weight here, some weight here, some weight here. So all these weights are now available to me. And I can then fine tune and these hyperparameters also to be able to get better performance, right? So here you can see this is how the weights are actually multiplied and then added. So for every layer, there's a weight attached. So you basically take that layer, then the value to predict, and add the bias to get the first neuron output. Similarly, for the second neuron, you add the particular layer weight, the value that I have to predict again, with adding the bias, and then final neuron output will be output of these two will be multiplied with the weights and then taking this output here. So this is how this is kind of stacked here. So you're multiplying the weight of this with this function, getting this value here. Here you multiply this, put it here. These outputs are given their weights and multiplied and added with a bias. The output is coming here. So I hope this is clear. So this is kind of breaking up the entire neural network that you have made. Now let's move on further. Now what do I want? What do I do if I have an image and I want to detect whether this is a cat or a dog? A classical problem, instead of having just numbers here, I have images here. Now it becomes a little critical. So I could say that, okay, I have certain data and I could just have outputs as 1 and 0 for because this is a binary output. I should be able to get 1, 0 for a cat, 0, 1 for a dog. If I have 10 outputs, I'll get values like this to be able to distinguish between all these numbers. So I have certain data and I have those associated labels, and these are categorical labels. So I have categories defined. Now let's try and do this using CNN. First, we'll move on to neural networks. So MNIST is a data set. I don't know if you people know it, but MNIST is about this particular data set that you have. You have numbers here in the MNIST data set, and you try and predict these number values from the image of the number. So again, I just have to say, import here the TF Keras data sets MNIST. It's a well-known data set, and it will be simply imported in the data value. So then I basically divide this into training images and its labels, validation images and labels by calling data.loadData. I then divide by 255.0. Why do I do it? Because it's a good idea. All my image pixels lie between 0 and 255. So I want these values to be kind of normalized. I want them to lie between 0 and 1. That is why all my images pixels are kind of divided by 255, both for the training and the validation images. Then I make a sequential model, just like we understood before. But here I have the first layer as a flattened layer. Now, why are we flattening it? You can see it here. So by flattening, I am able to get an image like this. So effectively, I have images like this. I have 60,000 labeled training set examples. I have 10,000 labeled validation examples. That's the data set we are using. Now, the size of every image. So what do? I kind of take every pixel. So if this is 10 by 10, I'll have 100 pixels of this. I will flatten it out as 100 pixels. Then similarly this, the next digit. So here what we have done is that we have 28 by 28 size. So I will flatten it. 28 into 28 is 784 or whatever the number it is. Yeah. So 784 is the number that you have. So I have all these pixels lined up like this. I hope it's clear to everybody. So we have flattened this image, input shape, and then I take a dense layer. Dense layer is where I'm connecting every neuron to every other neuron. I make an activation is ReLU. I think Rajiv Mishra sir talked about this also, where non-negative numbers are 0 and the output is positive. For positive is as per as required. Whatever is input is output as for positive numbers. So that's the activation function we use. And then we use softmax output because I know it's a classification problem. We use softmax as an activation and I just have 10 outputs. So this is my 10 outputs that I have. And these values will tell me which number it is. So it will be like this, these 10. So the first neuron, the second neuron, the third, fourth, and so on till 10th neuron, whatever value is output will be interpreted for that particular number. I hope the setup is clear. Any questions, anybody? Okay, so I'll move on then. So here, after doing this, we again compile the model. We have used another optimizer here, ADAM. The loss is sparse categorical cross entropy because we want the categories to have maximum difference between them. Two categories to have maximum difference between them. So they need to be separated. So the loss is kind of optimized according to the categorical value that we want. And metrics is accuracy. So these parameters you have already studied in the past with neural networks and all. So those are the same models here, parameters being used. We fit the model using training images. Training labels are given to us. We take 20 epochs right now. And then we see the results. So you can see here, the loss is this much. Accuracy for the training value is 0.97. And for accuracy for the validation is 0.96, which is not bad. But now I want to improve this also. So here you can start inspecting the values and everything, the weights and everything. This file is with you. You can take it back and you can see. These are just how the weights are added and everything is kind of broken down so that you people understand how this is actually running, right? So, and then if you have a problem, you can definitely get back to me. But since we are short on time, do you want me to discuss this? Or should I move on? Anyway, so I'll just move on because I guess we have faculty also in the class. So I think they should be knowing this. Anyways, now, so this is the kind of output that I get. So you can see here the accuracy for testing data becomes pretty less when it comes to images, but nevertheless, it's okay. Now I want to now improve this. So what can I do? I can either keep adding the dense layers, but what happens in dense layers? Now let's look at images. If I want to maybe distinguish between horses and humans. So this kind of a problem if I have. Now look at this. Every image has pixels. We already know that. So maybe if I have 600 pixels by 300 pixels and it's a color image, I will have 3 channels. So I will have 5,40,000 connections. And if I keep making dense layers, understand the quantum of connections that we will have. Just for single, we have this much. Then we will end up with very, very huge networks, and which will generally tend to overfit because every pixel is being kind of, given a weight, and every pixel is being tuned like a hyperparameter. So it becomes like it's going to be a very verbose kind of a network. So now you have to, anybody with a image processing background would understand that there are certain filters available. We have high pass filters, we have low pass filters, and they do certain work. So I think this would look familiar to everybody. We have a Sobel filter. What does it do? It gives us the vertical edges because this is a vertical filter. Similarly, if I have a horizontal filter with -1, -2, so something like this, if I have, okay, my pen is not working. So -1, -2, -1, 0, 0, 0, -1, -2, -1, it will give me horizontal edges. So I know that there are lots of filters available. What do? I generally do convolution of these networks, these filters, to be able to get some information out of this image. That is what we do. So suppose take an example like this. I have an image of a shoe here, and this is the image pixel values. If I have a filter like this, what will be the new value of the center pixel here? Center pixel will be this into this, plus this into this, the corresponding values, plus this into this, 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 plus this one, this one, this one, this one. So this is what your final value will be. So this is the new pixel value of the center pixel. Now this filter can be used to enhance the image to be able to understand certain features. So why do we do it? See, in typical image processing, what we used to do is, we used to take filters, we used to apply those filters, try to extract features out of it, take those features as values, and then train our model to be able to infer those values that we get from the filter. So those features we used to extract, and then we used to model them. Now the intelligent part here is that we are using filters here, and a lot of filters are being stacked together. So we have maybe 32 filters of different types, and we are trying to detect patterns. So this kind of a filter is here. So here it is trying to detect maybe a curve here. So every kind of a filter that we apply will detect something or the other, which is kind of prominent feature of that particular image that we are looking at. So that is why it becomes easier for us to be able to detect that. So here, suppose, like I said, you have vertical lines. So my idea is, if I have an image like this, which I'm not able to see, with certain filters, I may be able to detect a portion which gives me this part. Another part of the filter gives me this, which are easily recognizable for us as hands. Another filter gives me this part. And then I know that if I add all these values up, this may be a human. Similarly, if I am able to extract with this filter some feet like this, a head like this, a face like this, I know that it is a horse. So convolution neural networks basically extract features out of filters, and then they combine it to be able to make sense out of the label. I hope it's clear. So are you able to understand the idea behind CNN? Any problems, anybody? Please ask. If you feel free to ask if you have any problems. Okay. So here what are we doing is that we have feature extractor, we have a convolutional neural network, we extract those features out of this, and then we put it into a classifier. A classifier is still the dense network that we have. Now, how do we attain this? So we have some convolution network here. Conv2D is basically a convolution neural network. After applying this, I do some pooling. Now, what is pooling? So pooling is, see, what happens is after extraction of features, what will be the size if I have maybe 100 cross 100 kind of an image? What will be the size of the image that I get after filtering? It's going to be 99 cross 99, because you understand that the last part basically of any image is kind of left out, one column, because I will start from here, put my first filter here. If I have a 3 cross 3 filter, I will put it, so I will start getting an image like this, which will be have number of rows and number of columns, two less than the original image. So that is why it is still a big image that we have. Now what I want to do is I then generally do a pooling. So pooling is when I want to find out the maximum feature. There are two kinds of pools that we use: max pool, min pool. So here, suppose this is the output of the convolutional neural network that I have, and I do a pooling of 2 by 2. So it means take a matrix, take a pixel size filter of 2 by 2 and take the maximum value out of this. So 192 will be put here. Out of this, what is maximum? 144 will be put here. Out of this, 255 will be put here. Out of this, 168 will be put here. So this is the final output. You can see the size is drastically reduced. So the idea of a max pooling layer is to be able to extract the most prominent features after the convolution has been done, and reduce the size as well. So you do the pooling, then you again apply certain filters. Again, convolution 2D is done. And then again a pooling is done. After you've done this in certain iterations, you flatten this, because ultimately you'll have pixels, you will flatten them like before, then use a dense network, again use a dense network with a softmax for classification. So that's a typical classical neural network that we have. Let's see how we actually implement this. So this is the network that I have. Here we have taken, okay, I will use this one now. So we have taken the fashion MNIST data set. Now this has 60,000 training images and 10,000 test images of fashion and clothing items, and they have 10 classes each. So each image is a standardized 22 cross 22 size, and it's a grayscale image. So here we just load this fashion MNIST. It was okay. So now what I do is I again load the data set. I will divide by 255 like before. I make a sequential model of just flattening and with dense lenses. So let's see how does this perform. So right now we have not used convolution neural network. We have simply used the dense network like we used before. So it's going to take a little time. If anybody has any questions, please ask. You can take down these files and run them parallelly if you want. They're all available in the classroom. So while this trains, I'll just move a little further. So you can see that, the training and the validation is close to 89, 87% on validation, but yes, we can improve it. So we will start using convolutions like I discussed. Now, what do we do here? We import this again, the same thing. Here, the difference is that now I will have in the sequential model, my first will be conv 2D, and I'll have 64 filters of 3 by 3 size. So when I have 64 filters of 3 cross 3 size and my input shape is 28 cross 28 cross 1, my output will look like, because I'll have two lesser values, so 26 cross 26, and I'll have 64 such filters. So every filter will give me one output, so my size will be 64. They'll be all stacked together in one single stack with 26 cross 26, and 64 such values will be got because I have 64 such filters. I hope this is clear. So this is my first layer. Then I do a max pooling of standard 2 cross 2 size. So this will simply reduce the size by divide by 2 here. So this is 13 cross 13, and 64 layers will remain like that only. Then, because every image is being divided in two parts, so 2 cross 2. This I had explained here. So this is how your values are reducing. I hope it's clear. After this, again, I will take a convolution 2D network layer, 64 filters of 3 cross 3 again. We are using activation as ReLU here, which Rajiv Mishra sir had explained also. Again, max pooling I do. After this, I have put in a flatten layer. So after flatten will basically have, you kind of multiply all these values and you'll get this. So 5 into 5 into 64 would give me 1600 values. So they are put in single array now. So all this is flattened out. Then I use a dense network with 20 neurons here. And finally, since I want 10 outputs, I will use activation softmax and I'll get 10 outputs here. So this is my neural network that I have made using CNN. You can see here, the above model gave me similar, like whatever was said here, close to 86, 87, and 89 over here on training. Now let's try and use this model. And you will see that it goes up to 97 on training and 91% on validation, which is pretty significant and a step towards the right direction. This is what we want. Now, can anybody suggest me where can we improve? What can we do? So there are certain optional additional exercises which I have suggested. You can change, try to change the 32 to 16, 64. Try to see if we have more number of filters. Try to see how is it impacting the training time, the accuracy. Try to add more convolution layers. Try to add wider layers and make it more deep also. You can do this. It's up for you to try. And this is how it runs. I think it's okay. Is it okay? Any problems, anybody? Anybody wants to ask anything? So I have a convolution 2D network here. I did my pooling. Then again, I added another convolution 2D. And I applied a pooling, flatten, dense, and then another dense layer with a softmax output. So filters are now combined, and from the data, I am able to now make inferences. So how does it do now? It randomly initializes the filters. Now here, what we are doing, in each and every epoch, what are we doing? We are basically taking filters and we are giving them certain initial values. We apply them to the image, make a guess which one will match the label to the image, right? Like we had in the previous problem, here instead of giving values to the weight and the bias, we are changing the filters as well. The weights and everything are changing as well. Now check how many of your filters work to match the image to the label. So you're measuring your accuracy. You're trying to see. So maybe a filter which was edge detection gave you very good results. So you will try and see how far is it, how good is it. Then you optimize your guess like previously, use the data from the previous steps to tweak your set of filters. You will try and tweak a little bit in the values, the weights of the filters, and the kernel of the filter might be changed, and you will keep doing this till your desired number of accuracy is reached. Here we run them for a particular number of epochs. You could change the epochs and see if it is going towards overfitting. If it is working with lesser number of epochs, you have to run and see. So this is how the accuracy kind of goes down. So accuracy kind of increases, sorry. And the validation accuracy is also slightly increasing. But here it becomes a little stagnant after some time. So this is the model. Now, do you see a problem in this? What will happen in this? Any problems that you see, identify? So this is still running. Any problems that you can identify with this current module that you are running? So here it's written, normal data sets have images with background and are not centered, right? Because we took a fashion MNIST, I'll just show you how the fashion MNIST looks like. This is the kind of images that you have in fashion MNIST, you know. So they're pretty centered and you have very clear graphical images. They're pretty small, but then you can definitely make out what it is. But normal images that we see in our daily lives are not like this. The normal images that we see are not always centered. It's not always positioned correctly. The person may have a background. Then there may be a shadow involved. The color may not be very clear. There may be a contrast. So it may be at an angle. The pose may be different. So a lot of problems occur, and you can't fine tune every feature like this. So what do we do? So for this, we have something called image data generator. It's available with TensorFlow, and it's used for pre-processing the images. Now, what do? We take the set of images that we have. Now we're talking about a problems data set where we have horses and humans in images, and we are trying to distinguish between the two. So we take the entire data set of images, we divide it into two parts like we always used to do, a training part and a validation part. The training part will have two subfolders of horses and humans. And similarly, the validation part will have two subfolders of horses and humans. So generally, the validation for horses will be done with the training part of the horses, and validation of humans is done from the validation of the humans. That's how it works. Now the image generator, data generator, let's see how it works. I'll show you the file only. Let's see if it got trained. Yes. So you can see here almost 96.8, which is 97% accuracy in the training part, and 90.62, that is almost 91% accuracy in the validation part. So it is definitely better than the previous one. I hope it's clear. Now let's look at the augmentation part. Let's try and run this with the RAM that we have. Okay. So here, while this runs, we are basically using this API to be able to get the images from the horse or humans. It's a pretty well-known data set used. So I will put it here locally. And here we are simply just creating a data set, validation and training parts for both horses and humans. Now let's look at the model that we have. So model has convolution 2D, 32 filters of 3x3 size. And the input shape is 100 cross 100 cross 3. Why 3? Because this is a color image. So I have an RGB channel, and each image is of 100 pixels by 100 pixel size. Then I do a max pooling. Then again, convolution with 64 filters of 3x3. Max pooling again. Then I again do a 256 filters I again put in of 3x3 size. Again a max pool. Then I flatten everything out. Use a dense network of 512, then 256, and then finally into one layer, because I just have sigmoid output, 1 or 0. So I just need one output. It could be 0 and 1. So I'll just have one single neuron here in the end. I hope this model is clear. You can see the model. How does it look like? So the model has, like I said, convolution 2D, then max pooling, then another convolution, then again convolution and max pooling, convolution, max pooling, flatten, and then you have dense, and this is the final one with one output. So what was the, okay, so now I have to train this, compile. Okay. Now what are we doing here? So this is where it becomes a little different. Let's see. So I could have images of boots which may look very different from each other. They could be images like this, which can be confusing. Now this, when it is trained to look at images of shoes like this, if this comes as a shoe, it will not be able to detect. Similarly, if I'm training a cat images, the ears are pointed like this. They may be pointed at an angle, right? So they are not completely straight here. So it's tilted. So what do I need to do? I can rotate my initial image in such a manner. If I have images which are kind of rotated also, I'll be able to detect this. So what we do here, in this image data generation, we try and generate images using augmentation. So I'm adding certain rotation range. So till 40 degrees of a rotation range is available with me. If it is kind of available till a 40 degree, then it will be detected. So a rotation, so images are kind of augmented and then updated into the image data generator. So certain images are generated randomly by using all these augmentation techniques and put into your training data. Width shift range. So you could see examples here. So I can see what is happening here. If my full image is like this, I could basically have a half an image also. It could be at a certain height that I have, because it's a 100 cross 100 image. So not the entire image is here. So I can have width shift, height shift. This is also possible. I hope you are understanding this. Then, now this person is lying here, this person is straight. How do I get this? I can have a shearing parameter. So if my shearing is also allowed, so width shift, height shift, shear range of 0.2. So I can shear it out and I'll be able to detect this kind of an image as well. Here, what is happening? It's kind of zoomed in, because if this is the image, original image, I'll not be able to detect this. But if I add a zoom parameter, I'll be able to detect this. So we have something called a zoom range. Then if somebody's hand is, this left hand is up, then I could do a horizontal flip and get the right hand up, right? So otherwise what will happen? This image will not help me detect this one. But if I use this as a data set, then this might also be detected. So that is why we have a horizontal flip also. It is allowed. And here in the fill mode, you are trying to use the nearest parameter. Filling is whatever data is left. So here after sharing, you kind of fill with the nearest values available to complete the image of 100 cross 100. So this is known as data augmentation. I hope it is clear. So here what we do is, now we train the image. So we say the train data generator is now given to this function here, and it is giving me these ranges: rescaling, rotation range, width shift range, height shift range, shear range, zoom range, horizontal flip, fill, and the fill mode is given. Now what we do, just a second. Now we take a batch size here. So like I was saying, an epoch is what? It is the how many times am I seeing the entire data. Batch size is how many images are we taking in one time. So I'm taking 128 images in one time, right? So in my train generator, I take in batches of 128, I will generate these values. So all images now will be resized to target size is 100 cross 100, not 300 cross 300. And it is now generated. Then we have used this. We always do this rescaling, like I said before. And then we have a validation generator also for the target size this same. We again use the same validation folder instead of this folder, training folder. Once this is done, now you start training your model. So this is going to take time because this is a heavy model that we are looking at. So while this is running, let's try and see what is actually happening. So you can see here, this will give you a fair idea as to what pixels are actually being used to be able to detect between two images of a human and a horse. So this is how basically after filtering, this is how a human basically looks like, you know, after various filters of various levels. This is what is this, and the yellow part is actually being used. And when it becomes too large, you know, this is the structure that it looks at. For the horses, it will be a little different. So you can try this yourself. I started with a human. You can try with a horse image and then try to see what pixels, what structure does it look like. And ultimately, it looks for patterns. So if, you know, this is the kind of pattern coming for humans, the horses might be a little different. And then how it is able to distinguish between them. So every filter has a different output, and this is how it kind of interprets these patterns to be able to categorize horses and humans. So I think it's still running, but you will get a much better accuracy this time. Once this will run, we will actually see how the output is. So I will continue with this. So here we have been able to use different augmentation techniques to be able to detect images. So whenever we are coming to a CNN, the basic rule is to start with a simple baseline model, follow the convolution pool or the convolution pool pattern, which we have seen. We used convolution pool pattern. Use filters with odd sizes, 3 cross 3, 5 cross 5, 7 cross 7, because those would fit properly in your image. Because you'll have a center pixel very clearly defined there. Start with smaller filters to capture local features and increase their size. So we started with smaller filters, and then we are able to capture the local features. Here also, you can see in the output. So we are able to capture local outputs, and then we kind of increase the filter size as we move on. The number of channels should be low in the first layers. That's a thumb rule. Use padding to maintain the shape. We did not use padding, but padding can be used to preserve the size of the images. For pooling, we use 2 or 3 cross 3 kernels. We do not kind of reduce drastically the size, because out of 4 we are taking 1. Here out of 9 we are taking 1. If we end up taking bigger pool kernels, then we might end up losing a lot of information, which may be much useful for detecting certain patterns. So we do not want to lose upon that information. So that is why we use either 2 cross 2 or 3 cross 3 at the most. Keep adding layers until the model overfits. So we generally keep adding and then we try and remove the overfitting. That's what we do. Keep adding layers, so get inspired by other famous architectures. So architectures sir had discussed, so I will not go there. ResNet, GoogleNet, AlexNet, lots of architectures are available. You could simply use those architectures, do transfer learning. So transfer learning is basically when you take an architecture which is already existent, it's kind of trained, pre-trained. AlexNet is very popularly used. It is CIFAR ImageNet. It was used, I mean, that has huge database there. So it is used as, a kind of a landmark there. So you can use that, any trained model you can take up. Then just modify the last layer as per the output that you want. Hyperparameters can be tuned, so learning rate, activation functions that you have seen. So like a question was asked to me, now I can discuss that. So I can basically go a little bit about discussing that part also. Any questions, anybody? So like somebody was asking about summation, activation functions, I think. I can briefly go about this. Now, activation functions, we have generally these kind of activation functions, which are and then there are lots more, but for brevity's sake, I will just tell you. So we have a linear activation function, which is basically an identity, that's the basic one. Then you have a binary step one, where maybe you can define at which value do you want the function to switch from 0 to 1. So here, if you define it at 5, it will suddenly switch here. Sigmoid is of the form 1 upon 1 plus e to the power minus x, which takes this kind of a form, 0.5 for 1, and otherwise, 0.5 for 0. So when it is 0, it's going to be 1 divided by 2, 0.5. Otherwise, it takes this value. So kind of tends to 0, infinity when it's 0, and tends to 1 when it goes to positive infinity. Then tanh is also used at various places. This also has a similar output. ReLU, which was discussed by sir. So this is going to be 0 for all negative values, and whatever output is the similar as the input for all positive values. Softmax has this kind of a function here. So sample output is kind of shown here. So you can see here, it gives us, it is very good for categorization, for this value, it's giving me this here distinctly, there, here, 0.3 over here. So it's kind of distinguishing between the classes or outputs. Similarly, my optimizer, so I can have various optimizers also. So here the stochastic gradient descent is kind of used here. Back propagation. I think you people have already studied in this how the chain rule is applied. I think everybody is clear about this. So you have a forward back propagation, and in the back propagation, you basically take, this is the standard rule that you have. The new weight is the old weight minus meta times is the learning rate that you have, learning rate into the partial derivative of the loss with respect to the old weight. So this is how every weight is kind of modified in the back propagation. You go from here, and then when you back propagate, you change the weights according to the chain rule. And so every weight is kind of modified from the previous weights. And then you understand that there are various propagation paths. So suppose I want to find out this path, then I know that this is one route that I can have. This is another route from F31 to F21 to F12 to X1 in the back propagation. Then from F31 to F22 to F11 to X1. Then F31 to F22, then F12 to X1. So F31 plus F22, F13 and X1. So this is how the entire chain, kind of comes in play. So the back propagation is the weights are dependent on all the paths possible to this particular neuron. So you can see here, all these purple paths are taken into account. So many paths for every neuron. And then it rises to, that's not really a part of this course. So exploding gradient and all this. So, right. So I hope I just gave a brief review of whatever was actually done in the workshop already. But nevertheless, now you can see, so this is done here, I think. Okay, it's still running. But, so you have the files, you'll be able to run it. I'm sure, but you have any problems here, you just ask me. So this is how you basically build your CNNs. So here you can see, like I have an input here. I have convolution, then I have pooling, then I have again convolution, then again pooling. Then the same, pattern keeps repeating. I flatten it out. Then I have a fully connected dense layer. Then with fewer number of neurons, I have a softmax output. This is the typical feature. Now, how is it different? So CNN and multi-layer perceptron. Here, you have convolution, ReLU, pooling, fully connected layer. This is how it works. For multi-layer perceptron, you have input, you just have fully connected layers, and then you have output, which we saw. And you could see the change in the values also. You could see that this starts training better. Here, reduces the number of parameters by sharing weights. They have high number of parameters since it's fully connected. Every neuron is connected to every neuron. This is kind of sparse. It removes certain weights. It removes certain So here it becomes sparse because you are kind of reducing the number of connections here. This is relatively efficient because fully connected layers in last few, in the last few layers, you have fully connected layers. Like here, these are fully connected. Inefficient because of redundancy in high dimensions, fully connected parameter. The number of parameter also increases, the size increases, tends to overfit, and it tends to underperform. Computationally efficient for high pixel images, and this is very inefficient for high pixel images. So these are samples. You can see here, we don't have, this is a sparse connection. So you forego certain connections between the neurons of sequential layers. So this is a comparison of being able to predict zeros and crosses and knots. So X and 0 using CNN. So here, like you have, so augmentation would tell me it translates a little, it scales also a little, it rotates it also a little, because when we write, we do not always center our writing. So I can have a little X here. I could do a small one. I could maybe have a skewed one. I could have a fat one. So I do all these augmentations for both the X's and knots, and then I use them in the augmentation. Otherwise, what will happen, if this is what we are looking at, using this particular scenario, multi-layer perceptron, I will not be able to detect it. I hope this is clear to you, because it is, in that case, it will start matching individual pixels one by one, which will not give us the correct result. So here, you can see that it will start giving me errors. So here in the convolution, we have the filter, we do augmentation, and the pattern matching is done. So you apply various filters and you try to detect the patterns. So here you can see this ReLU is there. We've used ReLU pooling. So I guess this brings us to the end of this lecture. It's still training, but nevertheless, if you have any questions, I'm open to questions right now. So I think we'll finish this session here. Thank you.
Thank you, ma'am, for the wonderful session.